Okay. So how is everyone today? Good? All right. So today's, what, the 17th? Oops. 2018. All right. So last time we finished talking about whatever it was. We finished talking about. We finished talking about yeah, money. Yeah, that's right. Okay, good. Good. So now we're sorry.
So now we're back to rectangles.
Yeah. Well, no. Now we're on to something else entirely. Well, three-dimensional rectangles, anyway.
Okay.
So this is chapter 9.
Can I ask one quick question before we change subject?
Please do.
For the purposes of the test questions about the interest rate, the future value, when we're calculating the intermediate values where it's like e to the negative 0.4 or whatever,
Yeah.
how many decimal places should we truncate that to get the right answer?
Don't round at all in the intermediate,
Okay.
and then at the end round to the nearest hundredth.
Okay.
Do you have the dollar signs?
I'm not worried about it. You know, I mean, like, it's good to keep the units in mind. You know, like for example, when we were talking about the money thing, I carefully pointed out that the area is money because of essentially a unit consideration. So it's definitely like important, but I'm going to kind of like leave that to the chemistry, you know, and physics. Like, you know, you got to worry about units there. Here, you know, in math, you know, part of the strength of it is that you know, we can talk in sort of a unit-free situation. So I'm not worried about it.
And then notes for the last class. Yeah, those are posted.
Well, okay, as it turns out concerning last class, I believe I posted the PDF, but I forgot my camera that day, so then there won't be a video.
Okay.
But the PDF, I believe, is posted.
Yeah, it's I just want to make sure that printed it because your internet was down or something.
Yeah, it was, like last week. Frontier had some kind of something, I don't know. Other questions? Okay. So we're in chapter 9. So to kind of explain up until now, so this is like calculus for y'all up to the present time. So all the functions that we've dealt with have signature reals to reals. So what signature means is that it represents the kind of thing that is input to the function and the kind of thing that is output from the function. So all that I mean is, you know, for example, you know, here's the kind of function that we've dealt with. F of x is, you know, 13 x squared plus 26. Okay, so then the input to the function is x, and what kind of thing is x? Well, it's a number, right? A real number, it's one of those. And you take that x, the first thing you do is you square it, then you multiply the result by 13, and then you add 26. So what kind of thing is this? Also a real. So that's all that I mean. Is that we're talking about functions where the input is real and the output is real. Okay. Specifically, we've looked at the differential view. So the differential point of view for reals to reals. The differential point of view for reals to reals essentially is that, you take a function and you could say look at its plot. Maybe that's the plot of y is f of x. And the differential point of view is that if you choose a particular input, say that one, and you consider what the function does near that input, so if you look at it really close with the calculus eyeball, you're going to look at it really close there, then locally the function appears flat. So locally, specifically the function's graph is flat. Now, you got to be a little bit careful when you're talking to a mathematician or anyone who is like a specialist of any kind, because sometimes the way they use words is not the way that people generally use it, and flat is such an example. So to remind you, when a mathematician says flat, they don't necessarily mean horizontal. So, for example, the floor is flat, the wall is flat. They're both flat. But the floor is horizontal, and the wall is not horizontal. Okay, so then don't misunderstand this to mean horizontal. So the name of the local flat approximation to a function at a point is called its tangent line. So like the differential point of view is that locally things look like they're tangent lines. That's like a summary of calculus. So the best flat local approximation to y equal f of x is the tangent line. And then, of course, the slope of that tangent line can be computed with a derivative, which is why this is called the differential point of view. So notably, in order for the graph of a function to be locally flat, for this to make sense, the derivative has to exist there. So like on this red that I drew, does the derivative exist at every point? Well, at least, maybe according to the way I drew it, but I didn't intend for it to be the case. This is pointy. So because that location is pointy, that means that the derivative doesn't exist there. So here's the thing, is that, for example, like that point right there, if you were a little one-dimensional creature and you were on the red world right there and you were small enough, locally it would look flat. In the same kind of way that, if you were to literally go out to Kansas and get out in the middle of nowhere, it really does look flat. Or, you know, if you can imagine getting in a boat that doesn't sit very high off the water and going out into the ocean on very calm seas, it really does look flat. But if you were a little bitty creature and you were right there at the pointy place, no matter how small you get, it's still not going to look flat. It's going to look pointy, no matter how close you get. As a result, there is no local flat approximation to the function at that point, and as a result, the derivative does not exist there. Okay. So that's the differential point of view. So, you know, to some extent, the differential point of view is, you know, locally functions are flat as long as they're differentiable. Okay, good. So the integral point of view okay, which is like the flip side of the differential point of view for reals to reals. Is that the following? Is that the global signed area can be obtained by summing local signed areas. And then the picture, you know, is something like this. So if this is the plot of y is f of x, then the integral from a to b of f of x accumulates the signed area. You can kind of see that there's sort of like two different regions. There's that one and that one. One of these will be reckoned positive. Which one? The one that's above, and the other one negative. So the reason in the end why that's the case is because, for example, if you consider, say, this right here. Now the way I drew it, it looks like a line. Okay, it is a line, right? But let's, you know, do the calculus eyeball and look at it really, really closely, right? So that, you know, we can sort of like really see what's going on. The calculus eyeball point of view is saying something like this, that if you could see it close enough, it would actually look like this, that it's got a base, and it's pointing in the same way as the underlying space, and we're going to call that base dx, and then from, you know, you go to the right a little bit, and then you have to go up to meet the red. So then you go up. If this happens to be at a specific location x, then this would have height f of x. So what I'm telling you is that you know, the sort of imagination is that this is really just a really skinny, really thin rectangle. And, you know, remember the rule for the signed area of a rectangle. The orientation of the underlying space, the way that you indicate it, is by making a little swirl that first follows the first axis and then the second. So, you know, that's the orientation of the underlying space. So that one right there, we first follow dx and then f of x like so. So do you observe that the area of this rectangle is the product of those two, and it's positive because its orientation is in agreement with the underlying space. Okay, so this has a area. F of x dx, and that's going to end up being positive. Similarly, if we take this rectangle, of course it's just a line, right? But now I'll use again the calculus eyeball to examine it very, very closely. In this case, again, we follow dx a little bit. And then after we follow dx, do we go up or down? We have to go down, right, to meet the graph. So then we go down like that. And so what I'm telling you is that this line is really understood to mean a very, very thin rectangle. That kind of idea anyway. Again, the orientation of this area is we first follow dx and then f of x, like so. Do you observe that that is twisting clockwise, which is the opposite sense of the underlying space, which is counterclockwise? As a result, this rectangle has its signed area is negative. All right. And then, of course, to find the whole area, you just integrate, which is to say, let's add up all these little rectangles. Okay. So then, the differential point of view is saying that locally things are flat. The integral point of view, more or less, is saying that you can obtain a global property like area by adding up infinitely many infinitesimal local properties, the areas of these infinitely small rectangles. And area is a very abstract, can be as abstract as you want, including meaning money, right? So like we can find the total money flow, say, by adding up infinitely many infinitesimal bits of money. And we can transport it backwards and forwards to our desired time by, in the end, taking these little rectangles and moving them back and forth along a time axis. Good. Any question about this? Yes?
First one, just to find out how wrong I am.
Okay.
At the point, if you got the derivative of f of x, and then you evaluated it at the point where it's like the point
There?
you would get 0, right?
No. Let's not, what am I trying to say? Let's not speculate. Let's just do one. How about that? So, for example, okay. So in the first place, if you were to look at a plot, of y is x to 1/3, like so, then its plot looks like this. Now this is just expected knowledge. It makes this a nice looking S-curve. Okay, so that's just a fact. Now, if instead, if we take this, and I do y is x to 1/3, so right now it's exactly the same, and then I square it. Okay, so what that the effect that that's going to have on the plot is that, well, in particular, notice that the output on the left side is negative because it's below, but we're going to square it. So the effect of this is that it's going to take this side and sort of reflect it up. Okay, so as a result, I'm going to perform a little algebraic simplification. This is, usually written like this: x to 2/3 like that. So x with exponent 2/3. As a result, the plot will look like this. So that place right there is pointing. Okay. So now I believe your concern is that what will happen? What do we get if we compute the slope of the tangent line at the pointy place? It should be. My claim is that you can't do it. It sounds like your claim may be that it should be 0. All right. So let's consider the function. Let f of x be x to 2/3. Okay, so then, I guess the question is, please discuss the derivative evaluated at 0. In the end, that's the question. Okay, so then suppose we want to compute the derivative of this. Then what's its derivative? Very good. So that's just using the power rule. And then now, to write this in a slightly nicer way, instead of using a negative exponent, I'm going to do 1 over, so that it looks like this. And then instead of writing fractional exponent 1/3, I'm going to write cube root. Okay, so then are we all in agreement that this is the derivative? All right? So you tell me, can you plug in 0? You cannot, right? So then the case is that seeing that, you can see therefore the derivative evaluated at 0 is undefined.
So is that true for any time you have any effects where both sides are like concave, is going to be or like some on its own?
It's just going to be, it's just undefined. The question in the end is whether or not whether or not the thing is locally flat. Okay. In the end, that's the question. There's this. Now, the thing that, if I had to speculate, like, why would you have, before this example, why would you have thought that? Okay, so to be clear, I'll just remind you of some things, and that is that it is the definition of a critical point, and that is a critical point, well, let me say it like this. Let f of x be a function a critical point of f is any c technically to be to make this mathematically completely right, I have to say any c. And now I have to say something that's kind of weird. In the interior of f's domain, f's, let's say it like this, of the domain of f. So like this line usually is omitted from Math 1325, the line that says in the interior of the domain of f. Like that's like a technical point we just sort of gloss over. Such that one of the following is true. First, the tangent line exists and is horizontal. Okay, so that's one such possibility. In such a case, that means that the picture looks like one of these. So that would be something like that's point C there, and that's a critical point because it has a horizontal tangent line. So that's one possibility. Alternatively, it could look like this. But even there's a third alternative that many students, at least at first, seem to forget about. So such points. Sometimes the phraseology is calling this a smooth critical point. The other possibility is that the tangent line does not exist. So there's so many ways to not exist. So I'll just draw a handful of them. One of them is basically to locally look kind of like absolute value. So at that pointy place, locally, if you can imagine walking around, if you can imagine being a little one-dimensional creature walking around on the red world, where you can only look forward and backward, that's all you can do. No matter how small you get, that point right there is never going to look flat. It's always going to look like, oh, it's going, that one is like, when I turn to the right, it looks like this, and when I turn to the left, it looks like that. It doesn't look flat. So there's no tangent there. A different example that's even worse, in a sense, is a function, that does something like this, where it jumps. So that's even worse. The world fails to even be continuous there. So if I had to guess, then I'd guess that you may have joined these two into a single concept and thought maybe this was the only kind. These ones, if they're called anything, if these are called smooth, these ones are usually called non-smooth. Sorry? Technical? Oh, yeah. Yeah.
Is it really that's what it's considered? If it's like that, it's just non-smooth.
Yeah. Non-smooth. And sometimes these are called, sometimes these ones are called stationary. But in the end, the main thing is that concerning the graph of a function, it is either locally flat or it is not. If it's not locally flat, that's a critical point. If it's locally flat and moreover it's horizontal there, then that too is a critical point. So this is a failure to be locally flat. That's a critical point. And this one is locally flat and in addition to that, horizontal. That's also a critical point. In the language of, I wasn't your 1325 teacher, but in that language, it was probably something like the derivative either is 0 or doesn't exist. So this is the derivative is 0, this kind, and this one is the derivative doesn't exist. Okay, so then continuing this thought, okay, this is like a summary of what we've done. But notably, what I want you to take away from this page is that it's all been about functions that have signature real to real. Okay, so then if we like venture out and you know, other territories where that include functions of other signatures, then strictly speaking, what we've said doesn't hold for any of that. Okay, so this is here we are where we are now. So continued from 2 pages ago. Now we're going to deal with functions with signature r squared to r, and r cubed to r, etc. But the output is going to still be r, just r. So an example of this would be something like the following. So this function f of x is 13x squared plus 26. So that's what we wrote on 2 pages ago. This one has signature reals to reals, because you give it a single real input and it produces a single real output. But this other function, say like I don't know, h of x and y, we could use that to make, say, like 5x squared y plus 6x minus 8y. So what I want you to observe is that unlike what we were dealing with essentially up to and including last class were functions like this. Now notice this function has 2 inputs, 2 named inputs. One of them is x and the other y. All right. So what I want you to observe is that this input is in R2. All that means is that there are 2 real inputs. X is a real and y is a real. Now look what we're saying. We've given a formula, and look what it is that we're doing with the x and the y. We combine them in a formula, like an arithmetic formula, like the following. Now, what kind of thing is this? If you were to plug in a particular x and a particular y, what kind of thing would result? A real number. So, output is just real. So what I want you to see is that as a result of those considerations, this has signature r squared to r. So all of the calculus that we've done to now, none of it applies to this. This is a completely new situation. All right. So we're going to visit we're going to consider functions with signature r squared to r from the differential point of view and the integral point of view. Now, some of the particulars are going to be a little bit different, but the overall idea is the same. So now, specifically, when you look at the graph of a function, the dimensionality of the graph, like if you were a little bitty creature walking around on the graph, is however many inputs that you're given. So like when you look at the graph, a plot of the graph of y as f of x, then it's a one-dimensional thing. It's a one-dimensional thing because, well, you know, if you were happen to be standing right there, and you were little itty bitty, do you observe that you can only either go backwards or forwards? That's all that you can do. Because you just have that single degree of freedom. That's the same kind of freedom that you have on a line. A line is one-dimensional, so this plot is one-dimensional. Now we draw it on a two-dimensional plane, but that's only so we can make sense of it. Locally, it's a one-dimensional thing. All right. So this situation, because there's two inputs, that means that it's a two-dimensional thing. Its graph. Now we'll have to draw it in 3 dimensions so that we can make sense of it, to have a good look at it. But nevertheless, it's a two-dimensional thing. So like the surface of the world. If you could ignore things like buildings, right? If nothing could be like stacked on top of each other, like buildings, then the world is two-dimensional. You can walk around on it. In a sense, if you consider your local coordinates, you can either go forward and back, or left and right. That's all that you can do. If we imagine that you're not allowed to, climb on top of something or whatever. All right. Now, this is what we're going to do. But I want to make sure that you have sort of a clear view of calculus. So in other classes, but not ours, other courses, the second calculus course would also consider functions that do this, r to r2 and r to r3, etc. So that means that there's a single real input, but the output has multiple components. So here, what we're dealing with is that multiple inputs, single output. Now, all of the things that we've written on this page, on this remark, what I want you to see is that all of them have the case that either the inputs are scalars, that is to say there's a single input, or the outputs are scalars. There's a single output. So like this is, in some sense, where like the easy calculus ends. Because when there's permitted to be multiple inputs and multiple outputs, that's when things get interesting. So even later calculus courses, you deal with functions that have signature, stuff like this, R2 to R3, etc. Generally, as many inputs as you wish to as many outputs as you wish. That is where the fun begins. And well, I mean, that's what I like anyway. But well, there's even another place where the fun gets really exciting, and that is that when one of these or both, just one is enough, is almost too much. When one of these is infinite. So like you've got infinitely many components collapsing to finitely many, or the other way around. Then it becomes exciting.
Feel like it just keeps compressing.
Well, I don't know. I don't really have a way to. I don't really have a angle to go ahead to respond. But generally, all I want you to see is that the way calculus is taught and the way it was discovered is that, people figured out, oh, we're talking about functions. Okay, function, that's a useful concept. And then we figure out, oh yeah, a real input, a real output. Then people started saying, well, what if there were two real inputs? And, but the output is still just a single real. And, okay, what if there's a real input, but there's two real outputs? Okay, that's interesting. And then eventually you come to here. So like this setting right here is more or less where physics, modern physics occurs. That one. Okay. So, now, probably Thursday, I'm going to work on some drawing of the surfaces. But today, I want to remind you of some things that you already know from college algebra, just concerning drawings of functions with signature reals to reals. So this is plots for reals to reals. So what I'm telling you is that this page, this is something you already know, but so we're going to do it quite quick. And you need to know these and be ready for these on Thursday, because we're going to be drawing things on Thursday, and they're going to be two-dimensional surfaces drawn in 3D, and you're going to have a hard time looking at them, like an inordinately difficult time, if you don't know these. All right. So in the first place, we have lines. Functions that have this form. F of x is mx plus b. So I'll draw just three of them. Just so we get the general idea. So here's three separate lines. Okay, so specifically notice that each one of them is flat. And so just looking at the pictures, you should be able to tell me for each one, what is the sign of m? So what's the sign of m for this one? Negative. So m is negative. And how about for this one? It's 0. And this one? Positive. So all of these lines are flat, but only the one in the middle is horizontal, according to the math reckoning of those words. Similarly, just looking at these, you should be able to tell me the sign of b. So what's the sign of b for this one? Positive. And how can you see that? Exactly this. The question is where does it cross the y-axis? In this case, because it's above the origin, that means that b is positive. Yes. Well, it's the y-coordinate of the y-intercept. Right? How about this one? B is negative. And this one? Positive. And then, there's other combinations, like there's two other combinations, but I leave it to you to figure it out. No, there's more than two others, right? Well, if you were to do all combinations of m is negative, 0, positive, b is negative, 0, positive, then there'd be 9. But I leave it to you. Okay. We've got the power family of functions. Functions that have this pattern. F of x is x to exponent n for n is 1, 2, 3, ... Okay, so I'm going to draw 5 axes, 5 little bitty axes here. Okay, so then I'm going to just, what I'm going to do is I'm going to do f of x is x to n for n is 1, 2, 3, 4, 5. So f of x is x, and I'm going to come back and write the exponent in green. F of x is x, f of x is x, f of x is x, f of x is x. So I know that normally we don't write the exponent when the exponent is 1, but I'm just doing it so that the pattern is clear. So the function f of x is x to 1. Well, that's a line. So in some sense, it belongs in 2 families. It belongs in the family, that one, but it's also in this one. It looks like this. By the way, you know, these lines, they constitute almost all possible kinds of lines. But in fact, not every kind of line is represented here, because vertical lines are not represented here. Only lines that have slope are represented. So why am I not including vertical lines? It's not an omission, like I didn't forget. Okay. Well, I agree, but why not? Well, okay. You might remember from college algebra, there was some kind of visual inspection you can make on a plot to determine whether or not that plot represents the plot of a function. What is it? The vertical line test, right? The vertical line test says that if you look at a plot, this is an aside now. So if you look at a plot, say like the plot of a circle, you know, it's a reasonable question to ask, is that the plot of a function? Could a function make that plot? And the answer, in this case, is no. The answer is no because, well, this vertical line test, notice that that green line intersects the plot more than once. As a result, that couldn't possibly be a function. That's called the vertical line test. Now here's the thing. Consider a vertical line. Does it pass the vertical line test? No, right? Because it has to be the case that every vertical line crosses it 0 or 1 times. But if you take a vertical line and the vertical line you select is itself, how many times does a line intersect itself? More than once anyway, right? Infinitely many times. As a result, a vertical line is not a function. So vertical lines can't be in here, can't be in this list of plots of functions because it's not a function. Right? That would be like saying, you know, why didn't you include my giraffe in your picture gallery of dogs? Well, mainly because that's a giraffe. right? Not a dog, you know. I didn't include vertical lines in this list because they're not functions. Vertical lines? No. They're not. I promise you. Every input has at most one output. So like that's not a that's the circle is not a function because it has two intersections.
So the line you can draw a vertical line
Because well, so can we agree that this is a particular vertical line? Say like you know, maybe this is like you know, x is equal to 1. All right. So here's a, now I'm going to test the red. So I'm going to test it with, say, x is -2. So how many times does the green intersect the red? None. Okay, so it passes that much. And then if I was to move it over to like 0, how many times does x equal to 0 intersect the red? None. But my question is if I move the green to be on top of it, how many times does it intersect the red now? Infinitely many times, which is too much. Yeah, so it fails. So vertical lines are not functions. Okay, good.
How about that?
Yes, all of these are functions.
Oh, okay, yeah, that's all.
Okay, yeah, all of these are, yeah, but not the vertical ones. Okay, good. So now parabola. This one. We all know that shape. So I'll just draw it without comment. What I'd like for you to observe is a correspondence between algebra and picture, and that is that notice that, well, algebraically, if you square a positive thing, the result is positive, and if you square a negative thing, the result is still positive. That's why both sides of the plot are above the axis, because even when the input is negative, the output is still positive. All right? So the cubic, well, if you cube something positive, the result is still positive. But what if you cube something negative? It's going to be negative. So the cubic is going to be like this one, except this left arm is going to be down. So it'll look kind of like this. The left arm is down in the end because when you cube something negative, the result is still negative. One thing I want you to take away from this is that the cubic is flatter near the origin than the parabola. Okay, so the quartic will be like the parabola in the sense that both sides will be up, but it will be like the cubic in the sense that it'll be quite flat near the origin. So it'll look like this, and quite steep away from the origin. So it's like going really, it's going up really fast, way fast. Okay, but quite flat near the origin. And then how will the quintic look? Right. So it'll be like the cubic in the sense of one up and one down, but it'll be like the quartic in the sense that it'll be quite flat near the origin and quite steep, quite horizontal near the origin and quite steep away from the origin. All right. So now here's the thing that I want you to see is that there's a word called parity. Parity. And the way that you can use it in a sentence, as you can say it like this, is that the parity, parity of 8 is even. And and the parity of 13 is odd. So the word parity means evenness or oddness. Okay, and it's not parody, like making fun of something. So what I want you to observe about this family of functions is that the behavior is strongly influenced by the parity of the exponent. So notice that all of the odd parities, when the parity is odd, they all have the left arm is going down and the right arm is going up, right? Down and up, down and up, down and up. 1, 3, 5. Whereas when the parity is even, the left and right arms are both up. Both up, both up, and I didn't take the time to draw it, but the next one would be both up. Okay? Any question about the pattern? Okay, so the next one, the reciprocals. Reciprocal family. So these are the ones that look like f of x is 1 over x to exponent n for n equal 1, 2, 3. So again, I'm going to draw 5 axes, and I'm going to draw them right underneath these. Because I want you to be able to visually compare them. And we're going to do f of x is 1 over x to 1, but I'm going to come back and write the exponents in green. So f of x is 1 over x to 2. F of x is 1 over x to 3. F of x is 1 over x to 4. And f of x is 1 over x to 5. And again, I know that under normal circumstances when the exponent is 1, you don't write that, but I'm just doing it so the pattern is clear. So now, all of these things have a name, common enough, but perhaps the most notable name of all these is this one. This is a parabola. And this one is also so notable, the one that we haven't drawn yet, that it has a name, and its name also is something or other bola. What's this one? Hyperbola, right? That's what this one is. It looks like this. All right. Okay. So then, well, the reason why you can imagine, just discussing some of these reasons. If x is positive and getting bigger, then 1 over x is positive and getting smaller. So it's going to get closer and closer to 0, which is why this is like going to squeeze down. As you move to the right, it squeezes down. Similarly, notice that when you get close to x is 0, you get close to a division by 0, which of course is not permitted, mathematically. And you can kind of see this sort of like blow-up behavior here. That's kind of like a visual representation of no, you can't divide by 0, right? Causes things to blow up there. All right. At any rate, that's hyperbola. So now, moving one position to the right, instead of doing 1 over x, we're going to first square the x so that it's x squared, and then do 1 over that. So notably, if we were to make input a negative x, do you observe that we'd square it and get something positive and then do 1 over that? As a result, this one is going to look like that one, except what?
The left hand side will be on top.
Right, and it causes the left part to be high instead of low. So it looks like this. I'm also purposefully drawing another thing, and that is that this shape right there that you can kind of see, it's symmetric like a boomerang. Whereas this one, it is like someone took this area that's near the x-axis and sort of squeezed it, and most of it went, towards the y-axis, like. You can imagine that. All right, then the pattern just continues. That is to say, with the cube, notice that the cube doesn't. It preserves the sign of the input. So if the input was positive, the result is positive, and if the input was negative, the result is negative. So it looks like this. Okay, getting very squeezed there, and it just continues. But what I want you to take away from this is just, again, the parity issues. Parity strongly affects the result. Okay, one last family. These are the radicals. Functions with this pattern, f of x is nth root of x. But now instead of x starting at 1, instead of n starting at 1, n's going to start at 2. It's going to start at 2, because, we want to, that's the smallest possible radical number in the end. Like a second radical of x that is so common that it has its own special name. What's the special name for second radical of x? When n is 2. Square root, right? So there's not like a first root, right? That's not a thing. So you've got to start at 2. So I'm going to draw, instead of 5, I'm going to draw just 4, and I'm going to make them line up with these. Okay. So f of x is square root of x. F of x is cube root of x. F of x is fourth root of x, and f of x is fifth root of x. So now I'm going to write the radical number in green. So 2, 3, 4, 5. And of course, when the radical number is 2, you usually don't write that. Okay, so then the plot of square root of x looks like this. So I've got a question. Why is there no plot on the left? What can't be negative?
The root cannot be negative. The number inside the root cannot.
Right, the input, right?
Yeah.
You can't give a negative input to a square root. So that means that there's no plot over here. Okay. Now, to make sure something is clear, I hope. So have a look at this parabola, that parabola right there. Notably, what that's doing is it's squaring the input. And in some sense, the square root is like undoing that. So visually, the undoing of something, in this case, means to take the plot actually and reflect it like so. So to perform a reflection of inputs to outputs. What I'm telling you is that that much of the parabola is the same, but twisted and turned over as that much of the square root. So like they're the same. Now what I want you to observe is that, well, what if we like tried to keep both sides of the parabola? You know? This left side of the parabola, if we were to try and keep it, and since we've identified this part, that part of the parabola with that part of the square root, where would this part of the parabola go? It would go like this, right? Now I want you to imagine, what if that dash was actually there? Would the result be a function? No. It wouldn't pass the vertical line test. So in a sense, what the square root is it's, you know, you take the parabola, you surgery off the left side, so it's gone now, and then you twist it, and you get that much. And the surgery is necessary because otherwise the result would not be a function. Okay, so cube root. It's going to look like, specifically, we're going to take this thing and we're going to give it a twist. So it looks like this. So, you know, sort of, you know, similar to the cube root, but what else is there? I mean, similar to the square root, but what else is there? Like, what I'm saying is that this that I just drew is that right there. Can we draw the other side? Yeah. So it's there. So the cube root exists on both sides of the axis. Now, what that means is that it is in fact permissible to compute the cube root of a negative number. So, for example, what is the cube root of negative 8? Negative 2. Because, after all, negative 2 times negative 2 is positive 4, multiplied by one more negative 2 is negative 8. So, the cube root looks like this. What does the fourth root look like? It'll be like the square root in the sense that you only have a right side. But you know, it'll be like, you know, it'll be that part. It'll be, you know, it'll look a little different. Okay, how about the fifth root? How will it look? Like the cube root, in the sense that it's going to be on both sides. But, you know, it'll be kind of like the fourth root, in the sense that it's become quite vertical near the origin. Okay, so the whole point of this is to remind you of things that you already knew, but also to strongly remind you of the influence of parity on all these issues. So notice that they all have you know, like a characteristic kind of behavior. Like the even column has like this characteristic even behavior, and this odd column has its odd behavior, even behavior, odd behavior, and they just march on all the way to infinity. Good. Any questions about these? So I'm going to let this stew, you know, in your mind to think about this, because eventually we're going to need to be essentially like, if you can imagine it, there's going to be a parabola going like this, like that one is, and there's going to be another one coming in and out of the page. And it's going to be like a bowl, you know? Like you can imagine, just look down at your favorite bowl, you know, and just like take a marker and just draw one line one way, and then turn it a quarter turn and another line another way. Okay, I'll let that stew. For now, let's deal with some calculation matters. Okay, so for example, if oops, suppose that we have the following function. F of x and y is x squared plus 3 times x times y. Okay? So my first request of you is please evaluate the following. Please evaluate 2 comma negative 5. F at 2 comma negative 5. So what do you expect it is that I mean by this? Like, can you put it in just like plain language? What do I want? Yeah, just plug those in, right? Which is to say, well, in the definition of the function, x is in the first slot. So everywhere you see x, I want you to write a 2. And everywhere you see a y, I want you to write a negative 5. And then just, you know, just do it. So now, I'm going to make a recommendation for you, and that is that whenever you're going to do something like this, I encourage you to do the following. That you take this structure here, and you can see, oh, that's a thing, and that's a slot, and we're going to square that, and then plus 3 multiplied by, I'm going to write something in there, multiplied by a y, I'm going to write something in there. So I'm telling you that I encourage you to write out the parenthetical structure like that first, and then write the individual items in their places. Okay, so now, like that, and just so when you look at the notes, you can kind of remember what it was I was talking about, I'm going to leave that line there. So what I'm saying is that, in a sense, the first thing you do is write that first line, and then you fill these in. 2, negative 5. All right. So then you do that, and you get what? 4, and then negative 30. So this is negative 26. Now, you might complain a little bit and say, I don't know. I think my life would be easier if I didn't write those parentheses. Maybe I'm not going to do it. Okay. Well, I'd like for you to consider the following. So f of negative 3, comma, it doesn't matter, 8. So now I'm going to write something. But in fact, it's incorrect. And I see students do this a great deal, very often. So negative 3 squared multiplied, plus 3 multiply negative 3 multiply 8. Okay, so what I did is I more or less just didn't write the parentheses. Okay. Now this is actually incorrect. This is wrong. Now what's wrong about it? Right. So in particular, this is okay. This turns out to be okay. That one turns out to be correct. But in fact, that one is wrong. That one's wrong. And let's be clear about why it is wrong. So in the first place, when you write negative a, what that means, this means negative 1 multiply a. That's its meaning. All right. And furthermore, 2, when you write a squared, what that means, it means a multiply a. So like if instead of writing a squared, You know, we wrote like, instead of A to 2, if we wrote like A to 22, that would mean make 22 copies of A and then multiply them all together. Okay. So, as a result, the statement, you've got to parse the meaning of this. What that means negative 1 multiply 3, and then I'm going to write the, what is the punctuation for exponent? Caret, right? So that's how this parses. So we've got two operations here. We've got multiply and exponent. Which one occurs first? The exponent, right? Because the order of operations now I know that Miss Harris in 5th grade or whatever told you that the order of operations is PEMDAS, but actually Miss Harris is mistaken. That's not right. The actual order of operations is P, E, M and D are on the same level and they are resolved left to right. And A and S are on the same level and they are resolved left to right. So this M and D on the same level with left to right resolution, AS same level with left to right resolution. Well, I'll just say it like this. Any time that I'm on like social media, my friends and family, you know, they send me like aggravating math images, you know, I'm sure you've seen them, you know, where someone says like, you know, some kind of math thingy in an image. And one of the enjoyable ones is when you've got like this arithmetic expression that says, you know, evaluate what this says and then post your answer. Okay, and then some people are saying, it's 30, and then other people are saying, no, it's 4. You know, and it's all kinds of answers are all over the place. In the end, the reason is because, in the end, is that this is the correct order of operations, but what you learned in grade school is not right. Sorry. Maybe we'll have an exercise about this. Okay, but at any rate, can you see that it is the square that must occur first? That means that negative 3 squared is in fact equal to, well, it's equal to negative 1, 3 caret 2, like so, which is equal to negative 1 times 9, which is negative 9. But that can't be right because, well, just considering that term right there, if you put a negative number in, can we agree that a positive number should come out? As a result. Were you just double checking me there?
No, I was curious on the, because like on some of these you can do negative in 2 different ways. This one has like a specific negative sign.
Yeah.
So I was curious if it knows to, like if you do the specific negative sign and then a number and then square, whether it will do it correctly.
Yeah, so I mean, you know, it's a reasonable thing. Like, you know, there I've typed it in the machine, right? If I, you know, I'll press enter in a second, and you know, if I've just been, you know, if I've had it all wrong, it'll say 9. If I have it right, then it's going to say negative 9. Okay. Well, fine. So what I'm telling you is that here's the deal. Is that if you make the parenthetical structure like this, before you perform your substitutions, and then you write the things you're substituting into those parentheses, you'll never go wrong. It'll be right. Well, you won't make a mistake. You won't make this mistake. But let's acknowledge something that's important, and that is that you know, if you consider this one, this turns out to be okay even without parentheses. Why? Well, in the end, because those are all multiplies. That's why. So it turned out to be fine. The reason why this didn't turn out to be fine is because we substituted it into a slot, essentially, where there was an operation with higher precedence than multiply. Okay, so now I'll just evaluate this real quick. This is what, 9, and then plus, that'll be actually a subtract. So 9 minus 72, oh man, negative 63. All right, so what I want you to see is that if you always write the parentheses, you'll never make this kind of error. But also, some of the times if you don't write the parentheses, you know, you'll it's still okay because it still works out. And here's an interesting facet about human behavior, especially changing habits. And that is that if something works some of the time, if you have a habit where it works some of the time, it's extremely difficult to break that habit if it works some of the time. So I'm just telling you, you've got to stop not putting the parentheses, even though it works some of the time. Okay, and then I'm just acknowledging the difficulty that you may face in that. Okay, that being said, here we go. Would you please evaluate the following: f of x plus h, comma y. So specifically what I'm asking of you is I want you to, you know, everywhere you see an x in that expression at the top, I want you to replace it with an x plus h. And I want you to multiply it out and collect like terms. Okay, so then in the interest of time, here's my parentheses structure. So everywhere I see x, I'm going to write x plus h. And everywhere I see y, I'll write y. Okay, then I want you to multiply this out and collect like terms. So this x plus h all squared, that's something that you should just be able to just rattle off the answer. So what is it? If you were to FOIL it out or whatever.
X squared
Yeah.
plus h.
Uh-huh.
Plus h squared.
Very good. Okay, then distributing all that out, that would be 3xy, and then plus 3hy. Okay, very good. So, 4, would you please, f of x plus h comma y, and then subtract f of x, y, like that. Do that one. And you know, please reuse your previous work. Okay, so I'm going to write something. It's going to be wrong. So x squared plus 2xh plus h squared plus 3xy plus 3hy. Okay, so that's the first thing, and then I want to say subtract the original one, and the original one is that one, so subtract x squared plus 3xy. So the first one, subtract the second one. And what I have written is not right. The first one, subtract the second one.
The second one is not been followed.
Right, correct, right? Because notice that in the end, we've got this thing that's, you know, it's a subtraction. It's this, whatever this is, and then subtract whatever that is, right? So what I'm telling you is that this kind of substitution is just as necessary to use the same parenthetical structure as before. So what I'm saying is that, you know, you should have a parenthetical structure that looks like this. Blah minus blah. It should look like that. The one thing minus the other thing. So when you have it right, it'll look like, you know, x squared plus 2xh plus h squared plus 3xy plus 3hy, and then minus all this stuff. So notice the difference is that these parentheses right there actually didn't affect it, right? Adding them in didn't change anything, but these ones do change it, because this one, we're on this first line, this incorrect line, we're adding 3xy right there, but on this one we're subtracting it, and this is the correct one. Okay, so then if you cancel all available terms, do you observe that the x squareds cancel and the 3xy's cancel? And in fact, it is the case that the only terms that remain are the ones that have h's. So then you get 2xh plus h squared plus 3hy. Any question about this one? All right. Yes?
The number 3.
Yes?
The right hand, it's a 3 times x plus h times y.
Yes?
What's the exact order on, like, simplifying those 3 times 2?
I'm not sure I understand.
How do you go from 3 times x plus h times y to 3xy plus 3hy? What's the exact order?
Ah, well, I mean, I just kept them in the order that they appeared in. So 3 and then x and then y, and then 3hy. That's all that I did.
So when you distribute the 3, you put the 3 also in the parentheses, so like in parentheses 3x plus 3h.
Yes, you can. Yes, you could do it that way.
Okay. Because I did it without the parentheses, and then that's wrong, right? So you have to put it in the parentheses. Because if you just do plus 3x plus 3h, then only the y would go to the 3h.
Oh no, you can't do that.
Okay, so there has, when you're distributing the 3, it has to go in the parentheses with the x plus h.
Yes.
Okay.
If you like, you can imagine it like this. You know, this is just something, right? So, you know, call this a, so that it's 3ay. We could commute the y to the front to be with the 3, you know, because product commutes. So now it could be, what I'm saying is now, imagine the y is not there, and that this finger right here is covering up a 3y. Then that would distribute to the x, and you get 3yx. And it would also distribute to the h, and you get 3yh. Yeah?
Yeah.
Okay, good. Other questions? All right. So now, fifth, I want you to consider, suppose that we haven't made any consideration about h so far, but now I'm going to say, suppose that h is some number that's not 0. Please evaluate the following. F of x plus h comma y, subtract f of x y, and divide all that by h. So I'd like for you to take that expression and simplify it. So the question is what could we do to simplify this? Okay, so in the numerator, do you observe that every term has a h factor? So we could factor out an h in the numerator, and it would look like this. So what I'm saying is that in the numerator, we could do something that looks like this. And what I'm asking is that if we were to do that in the numerator, what do I have to write in the parentheses to make it right? What do you think? Right. If I want to take an h out of the numerator like that, what do I have to write in here? So like what if I take an h from that factor? It'd be 2x, right? So 2x, yeah, plus h, and plus 3y. Okay. So, okay, do you observe that the h's can cancel? But now here's the thing. You want to make a comparison here. So 2x plus h plus 3y. Now, specifically from here to here, my question is why can we do this? Why is that a permitted step? Let's think about this for a moment. Let's ignore all the rest of the context and just look at these two, and I'll refer to them as the top and the bottom. So notice that the top and the bottom expression all have three symbols, x, h, and y, x, h, and y. So this one has 3, that one has 3. All right? Now, the bottom one. Is it, for the bottom one, is it permissible to plug in h is 0 for the bottom one? Yeah. If you were to plug in h is 0, you'd have 2x plus 3y. Can you plug h into the top one? H is 0. The top one, this one. Yeah, so you can't plug in h is 0 to this one. Whoa. I must have hit something here. Huh. And I'm going to turn it off. come back. Okay. Now focus. All right. So can you plug h equal to 0 in this one? You can't, because you divide by 0. But you can plug h equal to 0 into this one. So that means that these two things are not the same. Because you can plug h equal to 0 into this one, but not that one. So why is it permissible for us to do that? In the end, because I said we're operating under the assumption that h is something that's not 0. That's what makes this okay. That's what makes that possible. All right. Six. Please compute the following. Please compute the limit as h goes to 0 of f of x plus h y minus f of x y over h. So of course, this thing right here, that's the answer to the previous part. So in the end, what I'm asking is what's the limit as h goes to 0 of that thing there. Okay. Well, what is it? Right. Because in this expression here, there's three symbols, x, h, and y, and the limit symbol is h. So h is what's moving, if you like. The x and the y, they just stay where they are. So they're constant with regard to h. So as a result, you just need to plug in h is 0. So I'm going to make an error. I want you to tell me what if you were to witness one of your friends write this answer down. Please, speculate as to what went in their head to have done such a thing. Yeah, I mean that's what it says. You're supposed to plug in 0, right? For h, not for all the stuff. Okay, just h. So this is oops. Only plug in h equal to 0. All right, so not that, but as y'all said, 2x plus 0 plus 3y. All right, interesting. What a boring sequence of things we just did. So wait, just to remind you, so we don't have to keep looking up, I just want you to recall that the definition of the function was f of x and y is x squared plus 3x y. That's what it was a page ago or so. I'd like for you to do the following. I want you to compute the derivative, compute the derivative of this expression with respect to x. And I want you, while you're doing this, I want you to do this while assuming y is constant. So y is just something that is constant. All right. So if we take this x squared plus 3xy, we can just do it term by term. So what's the derivative of x squared with respect to x? 2x. Okay, now this one's a little trickier, just a little bit. So what if that term was just 3x? Then what would its derivative with respect to x be? Just 3, right? Why 3? Well, let me ask it a different way. What if that 3 was like a 33? What's the derivative of, with respect to x, of 33x? 33. Okay. What's the derivative of like negative 8x with respect to x? Negative 8. Why? Because all of these things in front, these coefficients, they're constant with respect to x. Now, well, if we assume that y is constant with respect to x, then, you could imagine the 3xy, you could write it like this, 3y x. And all I did is I just wrote that a little bit over there so that I could, just do that. So if I was covering up an 8, the derivative of this would be, the derivative of 8x would be 8, right? And if I was covering up a 79, the derivative of 79x would be 79. What's the derivative of this with respect to x? 3y, because y is a constant. Can you see it? This garden path that we walked on, effectively what we did is we took this expression and we differentiated it with respect to x, but we were assuming that y was a constant. So that's what we did. So this is an important enough of a concept to have a name. So now we're going to give it a name. So this is a derivative for reals to reals and partial derivative for R2 to R. All right. So the reals to reals case, that's what you already know. That's what you learned in 1325. So in particular, if we have a function f that's a function of a single variable x, then we can denote its derivative with a prime, f prime. And then its definition is that this is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So you've got to remember that, derivative, after all, has a definition, and this is it. Okay, now, f of x plus delta x minus f of x, and then all that divided by delta x, what that is this thing that's inside of the limit, that's the slope of something called a secant line. I don't know if they talked about that a lot in 1325, but this is the slope of a secant line, and then when you allow the run to go to 0, delta x goes to 0, then what this is saying is that the slope of the tangent line is the limit of slopes of secant lines. Well, that's what it's saying. Okay, beautiful. Now, that's the definition in the real-to-real case. And in particular, we have two notations for this. You know, another way to write this is, you know, something like this. You could say d dx of f of x is f prime of x. I'm just writing down the notations that are in common use. So d dx, blah, blah. Okay, great. Now, here's the thing, is that in the R2 to R case, well, if you look at the previous page, notice that what we were doing is that the second argument was always just y. We just left it alone, right? But it was the first argument that's, you know, that was originally x that we were playing with to make x plus h. So we were playing with just the x's and leaving the y's alone. Do you observe that the situation is symmetric? We could have played with just the y's and left the x's alone? Okay. Because that's the case, in fact, we have two definitions. So what I'm going to do is I'm going to leave this box open. I'm going to write in that box in just a minute. So the first possibility is that we play with the first variable, x. And we say, okay, this will be f of x plus delta x comma y, and then subtract f of x comma y over delta x. So that's if we're playing with the x's. But we could just as well have played with the y's, right? So we have a separate thing, leaving myself another box. So the limit as delta y goes to 0, f of x, and then now y plus delta y, subtract f of xy over delta y. And we want, in a sense, just like in the reals to reals case, this is the derivative. Somehow these are derivatives. Now I'm going to write something, but if you're going to write it, understand that I'm going to edit it because I'm going to show you that it can't possibly be right. So this prime thingy is nice. What if we were to just like try to use it? What if we were to write f prime of x and y for that one, and I guess the same thing for this one. Now what's the problem with doing that? Okay, in case it, sorry? Okay, it makes it seem as if they're the same, right? So, well, let's consider this example real quick in this little, this little space I have here. What I asked you to do right here is I said, please take this expression, compute its derivative with respect to x, assuming momentarily that y is constant. Now let's do it the other way around. Let's take this expression, and let's differentiate it, but let's differentiate it with respect to y momentarily, assuming that x is a constant. Well, what's the derivative of x squared with respect to y if x is constant? What's the derivative of, like, say, I don't know, like 12 with respect to y? Zero. Why is it 0? Because 12 is constant, right? Okay. What's the derivative of 12,000 with respect to y? 0. Well, because 12,000 is a constant. What's the derivative of pi with respect to y? 0, because pi is a constant. What is the derivative of x squared with respect to y? 0. Why? Because x is constant. So what I'm telling you is that when you differentiate this term, you get a 0. And, well, how about this? What's the derivative of this with respect to y if x is constant? So x is a constant. 3x, right? Just cover up the constant bit. So are we in agreement that 3 is a constant? Yeah. And then x is a constant by supposition. So I'm covering up a constant. If I was covering up 5, I'd be asking, what's the derivative of 5y with respect to y? The answer would be 5. So the derivative of 3xy with respect to y is 3x. Now, do you observe that these are not the same? Here, this one was compute derivative with respect to x holding y constant. This one was with the roles reversed. Derivative with respect to y holding x constant. So, are these two the same thing? They can't be the same. Yet, do you observe that if we go with the prime, that can't work? Okay. So, you know, in the same kind of sense that, you know, if you have if it comes to pass that you have more than one child, probably would be, did you just say sorry? Sorry. Excuse me. If it comes to pass that you have more than one child, you might consider giving them different names. You know? Well, you know, like George Foreman has, you know, I think it's not an exaggeration. I think George Foreman has like 10 children.
Yeah.
And like they're like all called George. And you know, I've never met these folks. I'm sure they're very nice, but I imagine that's a little confusing. Whatever. So, in order to make this to keep sense of all of this, the way that this is denoted, we need to somehow make a mark that indicates that this is the one that was with respect to x, and this was the one that was with respect to y. Okay, so then the notation is a subscript x for the one that was when you were doing x, and this one is a subscript y for the one that you were doing y. What little thing? The tick?
Yeah.
No, it's not there. The tick mark is only permissible when there's a single variable.
So
Yeah.
N and then a subscript.
And then a subscript.
With the derivative of that function.
Yes. So in language, this is referred to as the partial derivative of f with respect to x. So that's what that one is. You could also just refer to it as the x partial, you know, if the rest of the stuff is understood. Similarly, this one is called the partial derivative of f with respect to y. And if the context is clear, it's usually just referred to as the y partial. So the word partial is chosen in the end because, this function has two inputs, but this one is only considering playing with the first input. So it only encodes part of the derivative information. So, and similar things about this one. So these are referred to as partials. Okay, good. So now, we're gonna start doing a whole bunch of these. Like, that's gonna be the next thing we do. But before we do that, we need to have just a little bit of notation to make it work right. And, in the reals to reals case, you can write this kind of thing, ddx of, I don't know, 7 x cubed plus the logarithm of x. So that's a totally, run-of-the-mill thing to write. So that d dx, well, that's the way you write derivative. Okay? So then I'll just do this really quick. Blah, blah, so 21 x squared plus 1 over x. Okay, nothing surprising there. Now what we want is we want an analogous bit of notation for partial derivatives. Okay, so like in the case r squared to r. So specifically, I want to be able to write something like, you know, I don't know, like 3 x squared y to 5, then, I don't know, minus, I don't know, the logarithm of y plus the exponential of x. Beautiful. And so we've got that expression there. And what I want to say, what I want to be able to write, is something like that d dx there. And I want it to mean the partial derivative of this with respect to x. That's what I want it to mean. And you know, at first, first consideration, you might just say, well, why don't we just use that? You know, if it does its duty there, why not do it here? In the end, there's good reasons not to permit that. So instead, we have a new symbol that looks similar to, but is distinct from that one. It still looks like d over dx, except now the d is written this way. So that's like a fancy looking d, okay? And those are different, and that's definitely not a 2. So that's a d, and that symbol is pronounced out loud depending on the in this context, it's pronounced as partial. In other contexts, it's pronounced as boundary, but I'm not going to go there, except just to say that there's other context to be had. This is how you write a partial derivative with respect to x. And you must, when you're going to use this notation, the d's must be that way. Now, the reason why I'm bringing this up is that, well, in the end, this is, if you write this, d dx, then what you're telling the reader, and in particular the grader, is that you're saying, I believe there is one variable and it is x. And now I'm going to differentiate that expression with respect to x. Whereas this statement, when you write this, you're saying, I believe there is more than one variable and one of them is x. So what I'm telling you is that, if, in the end, if you write the wrong one, you're like sending a signal to the reader, the grader, okay, about your belief about the how many variables there are, okay? So then it's a very significant matter. Now, that being said, the process works just like what you're used to, which is to say, I'm going to go ahead and work this one out. Just like this derivative operator is additive, so is this one, which means it just distributes to all the little bits. So, a first step might be to say, like this. This is the x partial of the first term, 3x squared y to 5, and then subtract the partial of logarithm of y, and then add the partial of the exponential of x. Now, when you get accustomed to doing all this, you usually don't write this intermediate step. You just sort of like imagine that one in your head. Okay, but I'm just doing it to show you that it works the way you expect. Now, we can, do them one at a time. So what is the x partial of this? Y to fifth, right? The reason why it works that way is because, well, y is a constant where this operator is concerned. So this partial x, partial derivative with respect to x, it is 3 is a constant to it, and so is y to 5. Yes?
So if it was partial y would be 3x squared, 5y to the fourth.
Yes. So what I'm saying is that these constant factors, because the derivative is homogeneous, they can be factored out. So now normally you don't write this, but I'm going to write it just so it's clear what's happening. This 3 can come out. That y to fifth can come out. So that that's what the derivative sees, in a sense. The 3 came out because it's a constant. The y to fifth came out because it's a constant. It's exactly the same, as long as it's constant, right? Good. As for this one, what is the x partial of logarithm of y? What's the x partial of like 10? 0. Why? Because 10 is a constant, right? Yeah. Logarithm y, does it depend on x? It doesn't. So this thing is constant. Now you got to be careful about that. Constant where this x partial is concerned. So when the x partial sees it, it just goes to 0. So subtract 0, and then now what's the x partial of exponential of x? Yes? Because that's a constant. Yeah. So logarithm y is constant with respect to x. Which is why this procedure is called partial derivative, because it doesn't encode all the possible derivative information.
So I have a question.
Yeah.
Y is 1 to the power of not 0.
It's a constant. I factored it out. Okay. So let me ask this. Going back to just a good old calculus. Like 1325. If I wrote this, 3 times x squared times 8, and I asked you to do that, then I don't know what you'd do in your head, but eventually I think you'd probably tell me that the answer is 48x. Eventually. Now I'm going to say that well, here's one way to go about it. That you could say that this is I'll factor out the 3 in the front. Because the factor of 3 comes out. And I'll factor out the 8 from the back. Factoring out the constant multiples is permissible because the derivative is homogeneous. So the real question comes down to, what is the derivative of x squared? The answer is 2x. So then the answer is 3 times 2x times 8. But of course, usually, all that occurs rapidly in your head, and you just come to 48x. But do you agree with all that I did there? What I'm telling you is that I factored the 3 out because it's a constant. I factored the y to 5 out because it's a constant.
It is multiplication, so that's why.
Right. Because it's
The other ones are subtraction.
right. Because yes, that's a subtraction. Right. Good. So then, what is the x partial of e to x? Just e to x. And then this, you could write this as what? 6x y to 5, and then leave the 0 and then plus e to x. Good. Any question about that? Okay. Now, one brief thing I want to just mention here, and that is, d and partial are different. So they're written differently. And they have different meanings. So they're not interchangeable. More or less, if you mix them up, then this is basically what you're running afoul of. Is that if you write the Latin d, the d that that one right there, then you're saying I believe that there's a single variable and its name is x. If you do that, etc. Similarly, the partial symbol and the number 2 are different. And I'm telling you this because here's the thing, is that the graders are not mind readers. And if it comes right down to it, and they can't tell if you wrote 2x or partial x or what have you, they're going to have to assume that you didn't know. Okay? Now, it might have been, it might be your experience that math folks, they're like peculiar, probably, maybe me especially. Okay, but especially like in the way that we write things. But in the end, it's reasons like this. Okay, so like I put little hats on my ones. In the end, so that when I'm writing, I don't confuse myself or someone else about absolute value. And my 2s, they've got this little fancy little thingy there. Okay, in the end, that's because of this. Okay, and there's just a multitude of other little bits. So I'm just letting you know. Good. Probably last one for today. Please evaluate the following. Partial with respect to w, say, why not? How about z cubed multiplied by the exponential of w squared plus 8, like that. Well, and then, maybe just for fun, plus 3w. So. Okay, so now, only because I'm up against the clock, otherwise I'd want to give you a little more time. I'll distribute the w partial, and furthermore, can we agree that z cubed is a constant? Okay, so then if you perform that distribution, then you come to this z cubed, and then w partial of exponential of w squared plus 8 and then plus, well, I think we can probably compute the W partial of 3W right now. So what is it? Plus 3. So now, the purpose of me giving this, this specific one at this specific place is to point something out. And that is that, well, all the rules that you learned before, like the fact that this one, d dx, is additive and homogeneous, so is the partial. And this one, d dx, it has to obey the chain rule. So does that one. This one has to obey the product rule. So does that one. So the point of putting this one right here is what's going to be required to do this? The chain rule. So specifically, what I want you to observe is that, well, if we were doing exactly the W partial of the exponential of W, then the answer would be the exponential of W. So if it was, if the that and that are in agreement. But what we're doing is that we're doing the W partial of the exponential of something else, U. So now these things are not in agreement, so W and U are not the same. As a result, the answer will be that this is the exponential of U. And then now to satisfy the chain rule, we have to multiply by the partial of U with respect to W. So that's the, this extra green bit, that's the chain rule. So what I'm telling you is that as a result of that, the answer is z cubed, and then multiply by that exact exponential, x squared, exponential of W squared plus 8. Okay, so we get exactly that exponential back. But now to satisfy the chain rule, we need to multiply by the partial with respect to W of W squared plus 8. And then don't forget the plus 3. So what I'm telling you is that those green bits are the same. So what's the, so 2W. So this would be z cubed exponential of W squared plus 8, and then multiply 2W, and then plus 3. So we'll do a few more of these next time. You know, we'll do ones that require the product rule and the quotient rule and all that beautiful stuff. Then we're going to draw some pictures, and then we're going to start calculating not tangent lines, but tangent planes. It's going to be so great. All right, have a nice Tuesday.